For over 200 years, the universe seemed well understood. Newton's laws of motion and gravity explained the movements of planets, falling apples, and even the motion of cannonballs. If you knew the position and velocity of an object, you could predict where it would be in the future. Time was absolute, ticking at the same rate for everyone, everywhere. Space was a vast, unchanging stage where events played out. This view of the universe worked remarkably well. Scientists could predict eclipses with precision, engineers could build machines based on Newtonian mechanics, and everything seemed logical and orderly. But beneath this comfortable picture, something was amiss. One of the biggest puzzles came from the nature of light. In the 19th century, James Clerk Maxwell formulated equations describing electricity and magnetism. These equations predicted that light was an electromagnetic wave that traveled at a fixed speed, about 300,000 kilometers per second, 186,000 miles per second. But this raised a troubling question. Relative to what? Waves usually need something to travel through. Sound waves need air, water waves need water. Scientists assumed light must also need a medium, which they called the luminiferous ether, an invisible substance filling all of space. If the ether existed, then Earth, moving through space, should experience an ether wind. This wind would make the speed of light appear faster or slower depending on whether we moved with or against it, just as the speed of sound changes depending on the wind direction. In 1887, American physicists Albert Michelson and Edward Morley designed an experiment to detect this ether wind. They built an incredibly precise device called an interferometer, which could measure tiny differences in light speed. They expected to see changes as Earth moved through the ether. But no matter how they adjusted their experiment, the speed of light was always the same. No ether wind was detected. This was shocking. How could the speed of light be constant? If Newton's laws were correct, moving observers should measure different light speeds, just like a person walking in the rain experiences raindrops hitting at different angles depending on their speed. With the failure to detect the ether, cracks in Newtonian physics began to widen. Some scientists, like Hendrik Lorentz and Henri Poincaré, tried to save Newton's framework by introducing complicated corrections. But nothing seemed to fully explain the mystery. Meanwhile, a young patent clerk named Albert Einstein in Bern, Switzerland, was about to revolutionize physics with a simple yet radical idea. What if the speed of light is always the same, no matter how fast you move? This single insight would change our understanding of time, space, and reality itself. Chapter 2: Einstein's Big Idea. A young man sat in a quiet office in Bern, Switzerland, surrounded by stacks of patent applications. His name was Albert Einstein, and he was not a famous scientist, not yet. By day, he worked as a clerk at the Swiss Patent Office. By night, he pondered the deepest mysteries of the universe. For years, physicists had struggled to explain why the speed of light never changed, no matter how fast an observer moved. The answer, Einstein realized, was shockingly simple. The speed of light doesn't change because time and space themselves adjust to make it so. This idea would rewrite the very fabric of reality. Riding a beam of light. Einstein had a habit of performing thought experiments, or Gedanken experiments in German. He imagined scenarios that stretched the limits of physics. One of his earliest thought experiments, when he was just 16, was this: what if I could chase a beam of light? What would I see? Classical physics suggested that if you moved at the speed of light, the beam should appear frozen, like a still wave. But Maxwell's equations said that light is always in motion. This contradiction gnawed at him for years. Then in 1905, it all clicked. The laws of physics do not change depending on how fast you are moving. The speed of light must remain constant. But if light's speed doesn't change, then something else must give way. And that something was time and space themselves. The two simple rules that changed everything. In his groundbreaking 1905 paper, Einstein laid out two fundamental postulates, two simple rules that would change our understanding of reality. 1. The laws of physics are the same for all observers, no matter how fast they are moving. Whether you're sitting on a train or standing on the platform, physics must work the same way for you. There is no special frame of reference where the laws of motion change. 2. The speed of light is always the same, no matter how fast you are moving. Whether you're standing still or racing at half the speed of light, if you measure a beam of light, you will always find it moving at exactly 300,000 kilometers per second, 186,000 miles per second. At first, these ideas might not seem radical, but their consequences were mind-blowing. If light speed is always the same, then time and space must stretch, shrink, and warp to keep this rule unbroken. Reality, it turned out, was not as rigid as Newton thought. It was fluid, flexible, and deeply intertwined with motion. The birth of relativity. Einstein called his theory special relativity because it applied only to objects moving at constant speeds, not accelerating. The word relativity means that things like motion, time, and distance are not absolute. They depend on the observer's frame of reference. For example, if you're sitting on a train and toss a ball straight up, it appears to move in a simple up and down path. But to someone standing outside, the ball follows a curved arc, since it is moving forward along with the train. Both perspectives are correct. They are simply relative to the observer. Einstein took this idea to its extreme. He showed that not just motion, but time and space themselves are relative. A person moving at high speed would experience time more slowly and distances differently compared to someone standing still. This was a revolutionary concept. It meant that time was not a universal, unchanging flow. Instead, it could stretch and contract depending on motion. With these ideas in place, Einstein was ready to shatter the very concept of time. Chapter 3. The Relativity of Time. Imagine two identical clocks, one on Earth and one aboard a spaceship traveling close to the speed of light. The clock on Earth ticks normally, but when the astronaut returns, something astonishing has happened. The clock on the spaceship has ticked more slowly. The astronaut has aged less than their twin on Earth. This is not science fiction. It is a direct consequence of Einstein's special theory of relativity. Time itself slows down for objects in motion. This phenomenon is called time dilation. But why does time behave this way? To understand, let's step into Einstein's mind and visualize time in a completely new way. The light clock experiment. Time slows for the moving observer. To grasp time dilation, imagine a light clock, a simple device with two mirrors facing each other, bouncing a pulse of light between them. Each bounce represents one tick of the clock. Now, let's conduct an experiment. One clock remains stationary. The light moves straight up and down. The other clock is placed on a spaceship moving at a very high speed. To an observer inside the spaceship, the light still moves up and down, just like in the stationary clock. But to an outside observer watching the spaceship fly past, the light follows a diagonal path, because the spaceship is moving forward while the light is bouncing. This diagonal path is longer than the straight up and down path. But the speed of light cannot change, it must remain constant. The only way for the light to travel this longer distance without breaking the speed rule is if time itself slows down for the moving clock. In other words, a moving clock ticks slower compared to a stationary one. This is not just a theoretical concept. It has been proven by experiments with high-speed particles and even astronauts aboard the International Space Station. Time dilation in real life. The space traveler's clock. Consider an astronaut traveling at 90% of the speed of light on a journey to a distant star. To them, the trip might feel like only a few years. But when they return to Earth, decades or even centuries might have passed. This effect, known as the twin paradox, highlights how motion changes the flow of time. The faster you move, the slower time passes for you compared to someone at rest. This has been confirmed with atomic clocks on fast-moving airplanes. Scientists placed identical atomic clocks, one on a plane and one on the ground. After the flight, the airborne clock had ticked slightly slower than the stationary one, proving that time dilation is real. At everyday speeds, this effect is tiny, But at speeds approaching the speed of light, time dilation becomes extreme. What this means for our understanding of time. Before Einstein, time was thought to be absolute, flowing the same way for everyone, everywhere. But special relativity shattered this idea. Time is not a fixed background, it is relative to the observer's motion. The faster you move, the slower time runs for you. There is no universal now that applies to all observers. This has profound consequences. It means that two people in different states of motion will disagree on when events happen. There is no single absolute reality. Each observer experiences their own version of time. Time is not what we once thought. It is not rigid or universal. Instead, it is flexible, woven into the very fabric of reality itself. Chapter 4. The Relativity of Space. Imagine a spaceship speeding past Earth at 90% of the speed of light. From the perspective of the astronaut inside, everything seems normal. The spacecraft's length remains unchanged, and all internal measurements behave as expected. But to an observer on Earth watching the spaceship zoom by, something strange happens. The spaceship appears shorter. This phenomenon is called length contraction, another mind-bending consequence of special relativity. Just as time slows down for a moving object, space itself contracts along the direction of motion. But why does this happen? Before Einstein, space was thought to be rigid, an unchanging stage where objects existed and moved. But special relativity showed that space, like time, is not fixed. To understand why, let's consider a simple analogy. Imagine a long train rushing past a station at nearly the speed of light. To a passenger inside the train, everything appears normal. The train's length remains unchanged. But to a person standing on the platform, the train looks shorter than when it was at rest. The faster the train moves, the more it contracts. This effect is not an optical illusion. It is a fundamental property of reality. Objects moving close to the speed of light actually become physically shorter in the direction of motion. The reason behind length contraction. Why does space contract for a moving object? The answer lies in the fact that the speed of light must remain constant for all observers. Let's return to our thought experiment with a light clock, except this time we place it horizontally inside a spaceship. If the spaceship is stationary, the light pulse moves back and forth between two mirrors in a straight line. But if the spaceship is moving at high speed, the light pulse must travel a diagonal path, since the mirrors are moving forward. Since the speed of light cannot change, the only way to account for this diagonal motion is if the spaceship's length contracts, effectively reducing the distance the light needs to travel. This contraction is not something you see with your eyes. It is an actual, measurable shortening of space for the moving object. Though length contraction is difficult to observe in everyday life, it has been confirmed in high-energy physics experiments. One striking example involves muons, tiny subatomic particles created when cosmic rays hit Earth's atmosphere. Muons have an extremely short lifespan, meaning they should decay before reaching the Earth's surface. However, scientists detect muons reaching the ground in large numbers. How is this possible? From the muons' perspective, their journey is much shorter because the Earth's atmosphere contracts in the direction of motion. This means that length contraction is not just a mathematical trick, it is a real effect observed in nature. What this means for our understanding of space. Length contraction tells us that space is not absolute, it depends on the observer's motion. The faster an object moves, the shorter it becomes in the direction of motion. At everyday speeds, this effect is too small to notice, but at speeds approaching the speed of light, it becomes dramatic. There is no single fixed reality. Space changes depending on how fast you move. Just as time is flexible and relative, so is space. The universe does not exist in a rigid framework. It bends and reshapes itself based on motion. Chapter 5. The Twin Paradox and the Nature of Time. Imagine two identical twin brothers. One stays on Earth while the other boards a spaceship that travels near the speed of light. After what seems like only a few years to the traveling twin, he returns to Earth, only to find that decades have passed for his sibling. The traveler has aged far less than his twin on Earth. This mind-boggling scenario is known as the twin paradox, and it is one of the most striking consequences of special relativity. But how can one twin age more slowly than the other? If all motion is relative, couldn't the space traveler argue that Earth was moving away from him just as much as he was moving away from Earth? Wouldn't both twins experience the same effects? To unravel this paradox, we need to examine the true nature of time and motion. Understanding the twin paradox, a journey through time. Let's break down the twin brothers' journey step by step. One twin boards a spacecraft and accelerates to a speed close to the speed of light, say 99% of the speed of light. The other twin remains on Earth, aging at a normal rate. The space traveler moves at nearly the speed of light for what feels like a few years to him. Meanwhile, back on Earth, much more time passes due to time dilation. The space traveler reaches his destination, turns around, and begins the journey back. Once again, from his perspective, only a short time has passed. When he arrives home, he expects to see his twin just a few years older than himself. But instead, his twin is now an old man, or worse, long gone, while the traveler has barely aged. At first, this might seem impossible. If motion is relative, why can't the traveling twin claim that he was stationary and the Earth twin was the one moving? Wouldn't both experience the same time dilation? The answer lies in one crucial detail. The space traveler experiences acceleration and deceleration, while the Earth twin does not. Why the twin paradox is not really a paradox. The key to resolving the paradox is realizing that the twins do not experience time symmetrically. The twin on Earth remains in an inertial frame. He does not accelerate or decelerate. His experience of time remains consistent. The traveling twin, however, undergoes extreme acceleration when departing, turning around and returning. These accelerations take him in and out of different frames of reference. Einstein's equations of special relativity show that during these transitions, the traveling twin's clock ticks significantly slower than the one on Earth. When calculated mathematically, without needing equations here, the effect of this time difference can be enormous. If the spaceship moves at 99% of the speed of light for a round trip lasting 10 years according to the traveler's clock, then over 200 years may have passed on Earth. This means the traveling twin has, in a very real sense, traveled into the future. Time travel to the future, a real possibility. The twin paradox demonstrates that traveling close to the speed of light allows a person to move forward in time relative to those left behind. This is not science fiction. It has been tested on a small scale with fast-moving atomic clocks. In the 1970s, scientists placed highly precise atomic clocks on commercial airliners and compared them with identical clocks that remained on the ground. The moving clocks ticked slightly slower, exactly as predicted by special relativity. Though the effect is tiny at commercial flight speeds, it would become enormous if we could travel at speeds approaching the speed of light. In theory, if a spaceship could sustain near-light speeds for long periods, an astronaut could travel thousands of years into the future while experiencing only a few years of personal time. Implications of the twin paradox. The twin paradox reveals deep truths about the nature of time. Time is not universal. It flows at different rates for different observers depending on their motion. High-speed travel is a form of time travel. Moving close to the speed of light slows down an observer's experience of time, allowing them to leap into the future. Acceleration breaks symmetry. The paradox is resolved when we recognize that acceleration and deceleration make the twins' journeys fundamentally different. This leads to profound questions. What does it mean to experience time? Could we build spacecraft capable of time travel? What would human civilization look like if people could travel into the distant future? While these remain open questions, one thing is clear. Einstein's special relativity has reshaped our understanding of time itself. What comes next? So far, we have seen that time slows down and space contracts for moving observers. But one of the most fundamental discoveries of special relativity is still to come. Nothing in the universe can move faster than light. Chapter 6. The Ultimate Speed Limit. Why nothing can travel faster than light. Imagine a futuristic spacecraft attempting to push past the speed of light. The engines roar as it accelerates, reaching 50% of the speed of light, then 80%, then 99%. The crew expects to break the barrier, but something strange happens. No matter how much energy they pump into their ship, they cannot reach or exceed the speed of light. This is not a technical limitation. It is a fundamental law of nature, dictated by Einstein's special theory of relativity. The speed of light, approximately 300,000 kilometers per second, is not just a fast speed. It is the absolute cosmic speed limit. No object with mass can ever reach or exceed it. But why? To understand, we must examine what happens as an object moves faster and faster. The energy problem. Why more speed requires more energy. When you push a car or a bicycle forward, you apply force, and the object gains speed. In everyday life, adding more fuel to a car or rocket allows it to accelerate faster. This is what Newtonian physics predicts. An object will move faster as long as we keep applying force. But at speeds approaching the speed of light, something extraordinary happens. As an object moves faster, it gains energy. But in special relativity, energy and mass are deeply connected, as we'll explore in the next chapter. The faster an object moves, the more its energy contributes to its effective mass. In other words, it gets heavier. At normal speeds, this added mass is insignificant. At 90% of the speed of light, the object's mass has nearly doubled. At 99.9% of the speed of light, its mass is hundreds of times larger than at rest. At 100% of the speed of light, the object's mass would become infinite, requiring an infinite amount of energy to push it even a tiny bit faster. Since no finite energy source can provide infinite energy, it becomes physically impossible for any object with mass to reach or exceed the speed of light. The nature of light. Why light itself moves at the speed limit. If no object with mass can reach the speed of light, why does light itself travel at this cosmic speed limit? The answer lies in the fact that light has no rest mass. Unlike objects made of atoms, photons, particles of light, are pure energy. This allows them to move at the maximum possible speed without violating the rules of relativity. If photons had even the tiniest bit of mass, they too would require infinite energy to reach light speed, meaning light as we know it would not exist. What would happen if we could break the speed of light? While no real object can exceed light speed, physics allows us to speculate about what would happen if something did. The consequences are bizarre. 1. Time reversal. According to special relativity, faster-than-light travel would cause an object to move backward in time relative to some observers. This creates paradoxes, such as the ability to alter the past, leading to logical contradictions. 2. Infinite energy requirements. Any attempt to accelerate past light speed would require infinite energy, which is simply unattainable in our universe. 3. Loss of causality. Causality, the idea that causes must precede effects, would break down. A spaceship traveling faster than light could, in some reference frames, arrive at its destination before it even left. For these reasons, modern physics treats the speed of light as a hard boundary that cannot be crossed. Evidence that the speed limit is real. Although special relativity predicts this speed limit mathematically, it has also been confirmed experimentally. Particle accelerators. In high-energy physics experiments, particles like electrons and protons are accelerated to speeds approaching 99.999% of the speed of light. Despite adding enormous amounts of energy, the particles never reach or exceed light speed. They only get closer and closer while their mass increases. 2. Cosmic rays. High-energy particles from space, known as cosmic rays, hit Earth's atmosphere at near-light speeds. Even these naturally occurring particles obey the cosmic speed limit. 3. GPS satellites. GPS technology relies on precise timing, which must account for relativistic effects. If special relativity were wrong, GPS would not function accurately. Yet, every calculation confirms that time dilation and the light speed limit hold true. What this means for space travel. If we are bound by the speed of light, does this mean interstellar travel is impossible? not necessarily. While traditional travel beyond light speed is ruled out by physics, there are theoretical workarounds, warp drives. Concepts like the Alcubierre drive propose bending space itself, allowing a spacecraft to surf on a wave of distorted spacetime, theoretically bypassing the light speed limit. Wormholes. Another speculative idea suggests shortcuts through spacetime, allowing near-instant travel between distant locations. Time dilation exploitation. While we cannot break the speed of light, travelers moving at relativistic speeds would experience much slower personal time, allowing them to reach distant stars in what feels like a short trip, though centuries might pass on Earth. These ideas remain purely theoretical for now, but they suggest that the cosmic speed limit may not be the ultimate barrier to deep space exploration. The profound implications of the light speed limit. Einstein's discovery that nothing can travel faster than light reshaped our understanding of the universe. It established a fundamental speed limit, defining the structure of spacetime itself. It linked energy and mass in ways never before understood, leading to new discoveries in nuclear physics and quantum mechanics. It challenged our classical ideas of absolute space and time, showing that motion and observation shape reality. As we move forward, another profound consequence of special relativity awaits us: the equation that changed the world, E = mc². Chapter 7. The equation that changed the world, E = mc². One equation, just 5 simple symbols, yet it encapsulates one of the most profound truths about the universe. E = mc². This equation is not just a formula, it is a revelation. It tells us that energy and mass are interchangeable, that everything we see, touch, and experience is, at its core, a form of energy, that the vast energy locked inside even the tiniest particles fuels the stars, powers nuclear bombs, and sustains all life. But how did Einstein arrive at this equation? And what does it truly mean? The hidden connection between mass and energy. Before Einstein, mass and energy were considered two separate things. Mass was simply the amount of stuff an object contained, measured in kilograms or grams. Energy was something entirely different: heat, light, motion, or electrical power measured in joules. But special relativity shattered this classical distinction. Einstein showed that mass itself is a form of energy, and energy can, under the right conditions, transform into mass. To understand how, let's break the equation down. E represents the total energy contained in an object. M is the object's mass, even when it is at rest. c², the speed of light squared, is an enormous number, 9 followed by 10 zeros, acting as the conversion factor between mass and energy. This equation tells us that even a tiny amount of mass holds an enormous amount of energy. For example, if you were to completely convert just 1 gram of mass into pure energy, it would release about 90 trillion joules, enough to power an entire city for a day. But how does this actually work? How mass becomes energy? The mechanics of E = mc². Mass-energy conversion does not happen under normal conditions. It requires extreme environments, such as 1. Nuclear reactions, fission and fusion. In the sun, hydrogen atoms fuse into helium, converting mass into light and heat. This is how the sun has been shining for billions of years. 2. Particle collisions. In particle accelerators, scientists smash protons together at nearly the speed of light. The energy of the collision creates new particles from pure energy, proving that energy can transform into mass. 3. Antimatter annihilation. When a particle and its antimatter counterpart collide, they annihilate each other, converting all their mass into pure energy. A tiny amount of antimatter could theoretically power an entire spacecraft. These processes reveal that mass is just a highly concentrated form of energy, bound within the structure of matter itself. Einstein's equation led to some of the most powerful scientific discoveries and some of the most terrifying weapons ever created. Every star, including our sun, burns due to nuclear fusion, which converts mass into energy. Without this process, life on Earth would not exist. The search for unlimited energy. Scientists are working to develop nuclear fusion reactors, mimicking the sun's power, to provide clean, limitless energy for the future. If successful, humanity could harness near-infinite energy with zero carbon emissions. What E equals mc squared means for our understanding of reality. This equation does more than explain energy production, it reshapes our fundamental view of existence. Matter is not solid. At a deep level, everything we see is just concentrated energy. Energy and mass are two sides of the same coin. One can become the other under the right conditions. Even empty space contains energy. The fabric of the universe itself is an energy field, which physicists are still trying to understand. Einstein's discovery paved the way for modern physics, leading to quantum mechanics, the study of black holes, and even theories of how the universe began. Chapter 8. Gravity as the bending of space and time, general relativity. In the late 19th century, Newton's laws of motion and gravity reigned supreme. Gravity was understood as a force, an invisible pull between objects. If you had two objects like the Earth and the Moon, their masses exerted a force on each other, and this force was what kept the Moon in orbit around Earth. But Einstein, having already upended our understanding of time and space with special relativity, asked a deeper question: what happens when gravity is involved? Newton's laws worked well for centuries, but they had their limitations, especially when dealing with very massive objects or objects moving at very high speeds. Einstein's answer would change everything, redefining gravity and launching a revolution in physics. The premise of general relativity. In 1915, Einstein proposed his theory of general relativity, which was a dramatic departure from Newton's concept of gravity. Instead of seeing gravity as an invisible force pulling objects together, he suggested that gravity is a curvature in space and time caused by mass and energy. To visualize this, imagine a rubber sheet stretched out flat. If you place a ball in the center, it creates a dent in the sheet. The larger the ball, the deeper the dent. Now imagine placing a smaller ball on the sheet. It will roll toward the larger ball, not because the larger ball is pulling it, but because the surface of the sheet is curved by the large ball. In general relativity, space and time themselves are like that rubber sheet, and mass and energy warp the fabric of space-time. The greater the mass of an object, the more it curves space-time around it. This curvature is what we perceive as gravity. Objects moving through curved space-time follow paths dictated by the curvature, just like the smaller ball rolling toward the larger one on the rubber sheet. This conceptual shift from force to curvature is the core idea of general relativity. How gravity is described by space-time curvature. Einstein's revolutionary insight was to describe gravity not as a force but as a geometric property of space-time itself. Space-time is a four-dimensional fabric that combines the three dimensions of space with the fourth dimension of time. Mass and energy distort this fabric. The curvature of this fabric dictates the motion of objects. A planet doesn't pull a moon toward it, but instead, the moon follows the curved paths in space-time created by the planet's mass. This bending of space and time is not just a useful analogy, it's a fundamental principle. To demonstrate it mathematically, Einstein formulated the field equations of general relativity, which describe how mass and energy influence the curvature of space-time. But even without delving into the complex equations, we can observe the effects of this curvature.
The bending of light.
A key test of general relativity. One of the most dramatic predictions of general relativity was that light would bend around massive objects. This is known as gravitational lensing. According to Einstein, the fabric of space-time curves so much around a massive object, like a star, that even light, the fastest thing in the universe, would follow this curvature. In 1919, during a solar eclipse, astronomers observed the deflection of starlight around the sun. This was a groundbreaking confirmation of Einstein's theory. Without general relativity, the stars near the sun during the eclipse should have appeared in their usual positions. But when they measured the position of these stars, they found that the starlight had indeed bent, just as Einstein predicted. The deflection was small, about 1.75 arcseconds, but it was enough to prove that space-time itself was curved by mass. Black holes, the extreme curvature of spacetime. Perhaps the most fascinating and extreme consequence of general relativity is the existence of black holes. In Einstein's framework, when a massive star collapses under its own gravity, it can compress into a point of infinite density known as a singularity. At the singularity, the curvature of spacetime becomes infinitely steep, causing the fabric of spacetime to curve in on itself. As a result, a black hole is formed. Not a hole in the traditional sense, but rather a region where the gravitational pull is so strong that not even light can escape. The boundary of this region is called the event horizon, and once anything crosses it, whether it's matter or light, it is lost forever to the black hole. The presence of black holes was initially theoretical, but in recent years we have found indirect evidence supporting their existence, including the detection of gravitational waves from black hole mergers. Gravitational waves are ripples in spacetime itself, predicted by Einstein, and their discovery in 2015 confirmed that general relativity was accurate even in extreme situations. In addition to curving space, mass also warps time. This phenomenon, known as gravitational time dilation, occurs near very massive objects like black holes or neutron stars. Imagine two clocks, one on Earth and another placed near a massive object like a black hole. The clock closer to the black hole would tick slower than the clock on Earth. To an observer far away from the black hole, it would appear as if the clock near the black hole was moving in slow motion. This is because the intense gravitational field near the black hole causes spacetime to stretch and distort, affecting the passage of time. In 1976, the GPS system, which we rely on for navigation, had to account for the fact that satellites in orbit experience less gravitational time dilation than clocks on Earth. If this was not taken into consideration, the GPS would be inaccurate by several kilometers. This is a real-world example of how general relativity affects our daily lives, even though we may not see it directly. The expanding universe and general relativity. Einstein's theory of general relativity didn't just describe objects like planets, stars, and black holes. It also had profound implications for the very structure of the universe itself. In the early 20th century, the universe was thought to be static and unchanging. But in 1917, Einstein introduced a cosmological constant into his equations to allow for a static universe. However, this assumption was soon proven wrong by the work of astronomer Edwin Hubble, who discovered that the universe was actually expanding. After Hubble's discovery, Einstein discarded the cosmological constant, but his equations still described a dynamic, ever-changing universe. The equations of general relativity could now be applied to cosmology, leading to the understanding that the universe itself was evolving, expanding, and that the Big Bang could be traced back to a singularity, a point of infinite density. The legacy of general relativity. Einstein's general theory of relativity fundamentally altered our understanding of space, time, and gravity. It is one of the cornerstones of modern physics, and is essential to technologies like GPS. The theory has stood up to rigorous experimental tests and continues to be validated by observations of cosmic phenomena. But even Einstein could not have predicted the full implications of his work. Today, scientists are studying how general relativity interacts with quantum mechanics, leading to the search for a theory of quantum gravity. Chapter 9. Drawing parallels between theory of relativity and Hindu mythology. In a world where science often seeks answers through equations and experiments, and spirituality through introspection and ancient wisdom, a fascinating parallel emerges between Einstein's theory of relativity and the timeless teachings of Hinduism. Both challenge the conventional perception of time, space, and the self, one through the lens of physics and the other through metaphysics. This story journeys through the realms of space-time and sacred texts. Long ago, during the age of kings and cosmic wars, there lived a mighty ruler named Muchukunda of the Ikshvaku dynasty, a noble and powerful lineage said to descend from the sun itself. Muchukunda was a righteous monarch who ruled the earth with wisdom and valor. But his destiny was not confined to the soil beneath his feet. A time came when the Devas, celestial beings who govern the heavens, found themselves outmatched by the powerful Asuras, demonic forces threatening the balance of the cosmos. Desperate and defeated, the Devas turned to King Muchakunda, a mortal, yet a warrior of unparalleled strength and virtue. Moved by their plight, Muchakunda left his earthly kingdom and rose to fight alongside the Devas. The battles he fought in the celestial realms were not of days or months, but of ages, though in the divine plane they passed like fleeting moments. Muchakunda fought for what seemed to him only a few years. But the Devas knew, on Earth, time was not the same. When peace was finally restored, the Devas offered Muchakunda a boon. He asked for nothing but rest. He had been denied sleep for many years during the war and wished for undisturbed slumber. The Devas, in reverence, granted him his wish, and a curse to go with it. Anyone who dared awaken him would be reduced to ashes. But before departing, they revealed a truth that stunned him. "O King, while you fought beside us, many yugas have passed on Earth. The world you left is no more. Generations have come and gone. Humanity has changed. Your kingdom, your people, your family, all are but dust now." Muchakunda stood silent. For him, only a few short years had passed. But on Earth, thousands of years had flown like leaves in a storm. Bewildered but exhausted, he descended to Earth and entered a deep cave to fulfill his final desire: rest. The Awakening. Much later, perhaps in the Dvapara Yuga during Lord Krishna's time, a barbaric invader named Kalayavana chased Krishna, who led him into the very same cave where Muchakunda lay sleeping. Mistaking the sleeping king for Krishna, Kalayavana touched him. In an instant, Kalayavana was burned to ashes, and Muchakunda awoke. As his eyes opened, he looked around at the world and realized everything was different. Humans were smaller, weaker, and their way of life was alien to him. Civilizations had risen and fallen. Entire ages had turned their pages. The world he once knew had faded into legend. Why did time flow differently? The Hindu explanation: multiple realms, multiple clocks. According to Hindu cosmology, the universe is divided into many locus realms, each with its own laws, energies, and most importantly, its own flow of time. In Buloka, Earth, time is dense and slow. We live and age in years and decades. In Devaloka, realm of the gods, time is more fluid. One Deva day equals one Earth year. In higher realms like Mahaloka, Janaloka, and Brahmaloka, time is even more dilated. One Brahma day equals 4.32 billion Earth years. The higher the realm, the more refined the vibration, the slower time flows relative to Earth. Muchakunda did not merely stay in Devaloka. He likely ascended into higher celestial planes during his service to the gods. Even if he spent only a few divine years, it would amount to thousands of Earth years. Furthermore, his long sleep in the cave, possibly magical or suspended in some yogic trance, contributed to even more Earth-time passing. Scientific parallel: Einstein's special theory of relativity. In Einstein's special theory of relativity, time does not flow uniformly. It depends on speed. Time slows down for someone moving near the speed of light. Frame of reference: two observers in different states of motion experience different durations of time. Imagine an astronaut traveling near the speed of light for a few years. When they return to Earth, centuries may have passed. This is called time dilation. Muchakunda's myth mirrors this idea. He is removed from Earth's time frame. He enters a different cosmic reference frame. When he returns, the world has aged, but he hasn't. Though the ancients didn't use equations, the concept is the same. Conclusion: a timeless tale of time. The story of King Muchakunda is more than myth. It is an intuitive, poetic expression of a truth modern physics would confirm millennia later. Time is not absolute. It bends, stretches, and dances with motion and perspective. Muchakunda was not just a warrior or king. He was a traveler through time, caught between cosmic clocks, a mythic echo of the relativistic universe Einstein revealed to us. Let's talk about another similar story from Hindu textbooks. The Cosmic Voyage of King Kakudmi and Revati, a story of time, space, and relativity. Long ago, in a world untouched by decay and distraction, where Dharma guided every step and the air shimmered with spiritual clarity, there lived a noble and just king named Kakudmi. He ruled the magnificent city of Kushasthali, a kingdom said to be more radiant than gold, nestled in the folds of the Satya Yuga, the first and purest era of existence. Kakudmi was no ordinary king. He was wise, composed, and had a daughter named Revati, who was the very embodiment of perfection. Graceful, powerful, and profoundly intelligent, she was unlike any woman of her age, or perhaps of any age, and therein lay Kakudmi's dilemma. He sought a husband for Revati, a man who would be equal to her in spirit and strength. But across the earth, no suitor seemed worthy. Thus, King Kakudmi decided to do what no mortal had dared before. He would seek divine counsel, not from priests or sages, but from Lord Brahma himself, creator of the universe, who resided in the celestial realm of Brahma Loka. With the help of ancient mantras and divine permission, Kakudmi and Revati journeyed upward, not into the sky, but into higher dimensions of existence. In Hindu cosmology, Brahma Loka is not a planet, it's a higher plane, existing beyond normal space and time. In modern physics, this resembles the idea of higher dimensions or non-Euclidean spacetime, regions where gravity, time, and reality behave very differently. As they entered Brahma Loka, they found themselves surrounded by lightless brilliance, divine music, and an energy unlike anything on Earth. Time felt slow, or perhaps irrelevant. Lord Brahma was attending a celestial concert performed by the Gandharvas, angelic musicians. Out of respect, Kakudmi and Revati waited, and they waited. What felt to them like perhaps an hour or two passed. When the performance ended, they approached Lord Brahma and humbly asked, "O Creator, we seek guidance. Who in this world is worthy of marrying my daughter?" Brahma's response was both kind and bewildering. "Dear King, while you waited here, 27 Chatter Yugas have passed on Earth." Kakudmi's heart stilled. Each Chatter Yuga is about 4.32 million years. So 27 Chatter Yugas equals 116 million Earth years. This aligns beautifully with Einstein's concept of time dilation, the idea that time passes differently for observers in different frames of reference. In this case, Kakudmi and Revati had entered a realm where time flowed extremely slowly, just as astronauts near a black hole or moving at near light speed would experience minutes, while centuries pass for those left behind. Lord Brahma explained that all of Earth as they knew it was gone. The kings, the kingdoms, the cultures, all had vanished into dust and legend. But all was not lost. A new age had dawned, the Dvapara Yuga. And in this time lived a noble and divine soul, Balarama, the elder brother of Krishna, born to restore balance to the earth. Brahma said that he would be a suitable match for Revati. When they descended from Brahma Loka back to earth, they found a world unrecognizable. Their kingdom was gone. The language had changed. The people were smaller, weaker, more fragile than Revati, who, being from Satya Yuga, was taller and stronger, almost like a titan among mortals. Scientific parallel. This also reflects what relativity predicts. If someone travels through time at near light speed, when they return, they will be out of sync with Earth. Not only will more time have passed, but the entire civilization, biology, and environment may have evolved. To adapt to this new earthly reality, Revati's form was reduced, symbolically, perhaps through divine intervention, and she married Balarama, fulfilling the path of destiny. The scientific takeaway, relativity in ancient garb. Let's decode the science within the story. 1. Time dilation, Einstein's special relativity. Kakudmi and Revati experience a short period of time in Brahma Loka. But on Earth, millions of years have passed. This is like the twin paradox in physics. If one twin travels near the speed of light, they return younger, while the other has aged. 2. Gravitational time dilation, general relativity, time altered gravitational fields. Brahma Loka, being far removed from material existence, could represent such a region where time is dilated compared to Earth. 3. higher dimensions. The journey to Brahma Loka parallels the concept of entering a higher dimensional realm, much like theoretical physics describes with multiverse models, branes, or quantum layers. Conclusion: a myth that echoes modern physics. The story of King Kakudmi and Revati is not just a tale of gods and time, it is a deep, intuitive grasp of the universe's most mysterious laws, cloaked in myth and metaphor. Long before Einstein, this story taught us that time is not absolute, that traveling to a different realm, even waiting a short while, could mean returning to a future where everything you knew is gone, that space and time are flexible, flowing differently depending on where you are in the cosmos, and that sometimes mythology and science are not opposites, but parallel ways of understanding the same cosmic truth.